exam 3, the equation sheet is posted. The exam 3 review is also currently posted. So if you have specific questions about that or about the material, it's there, the same format as the last two. So, you know, it is what it is, but it's going to be about AC stuff. We'll have a dependent question, and then you'll have an inductor and a capacitor question. So before we get into the inductors and currents, last time we were kind of at this point here. So we went through, we talked a little bit about Lenz's law, which is not necessary for the exam, but that is going to go through, and that is why for our induced voltage value inside of the inductor, it is a time derivative for the current, where in particular for that current and the voltage, they're instantaneous values to go through and find those relationships. And then we have our series and parallel equations for inductance, which look similar to, or how we go through and do that is the same way we do for resistors. So any questions on last time? All right, so today we're going to talk about inductors and DC and AC circuits. So because our equation for, if we, right, just look at this equation here really quick, we have a time derivative in here. So if we think about what we were doing with capacitors, over time we were building up voltage, and that caused our capacitor to look like a brake. When it comes to inductors, if we look at, again, long periods of time, aren't necessarily actively long periods of time, what we'll go through and have is we'll have constant current. And when we have I being constant, what is the time derivative of any constant? So there would be no voltage. And so when we have a constant current, there's no induced voltage. And so we would be able to treat our inductor like a short. We can treat it like an ideal wire. This is especially going to be the case when we have a DC current. So with an alternating current, because we're going to constantly be changing the values, we'll never have a time derivative value equal to 0. But for DC, we can go through and again, look at a time constant. And with our time constant, if we think about for the RC circuit, tau is just equal to RC. For the RL circuit, the time constant is going to be the inductance value divided by the resistance. So we'll take, again, technically with these are going to be LT and RT. If we go through and do the unit analysis on it, we are going to find that because this is also a time constant, it has the SI units of seconds. So if we plug in the inductance in Henry, our resistance in ohms, this will pop out in seconds. So the equation does look different, but the idea of going through and using this time constant value is going to make it such that our equations for the RC and the RL circuits look relatively similar to each other. So because we're gonna, in this case, for right now, we're just gonna look at the resistor and inductor in series. This means that they are gonna have the same current. Now, something that we are gonna get to next week is we are going to look at RL circuits in series and in parallel. when we're gonna go through and do those, our inductor and our resistor are always going to be in series with each other. Just now we'll have two sets of inductors and resistors, or capacitors and resistors, and we'll deal with them in their separate ways. So can somebody explain to me what the current did as a function of time when we had a resistor capacitor circuit? What did the current do over time? Yeah, so it had that exponential curve to it. It is the opposite for an inductor. So as time progresses, that time derivative portion gets closer and closer and closer to zero until it eventually becomes zero. So our current is actually going to increase as a function of time, and it has that exponential curve. And if we look here once again, we see that we are measuring our time in taus. So we have 1, 2, 3, 4, 5 taus. And at 5 tau, so again, 5 time constants later, we are said to be at 100%. It's close enough. So again, we're going to be seeing 5 tau being represented as a long period of time for that particular circuit. So 5 tau, still considered a long period of time. If this is the case, the current value that we should be getting, if we're treating our inductor like a short, you have a single battery source, because again, this is for DC, single battery, single resistor, we can utilize Ohm's law to find that current value. So with the capacitor, right, we were able to store energy in terms of the electric field by having those charges separated. If we go through and we look at inductors, they have energy stored in terms of the magnetic field. So if I am now to take out the battery, I'm going to start losing energy inside of that inductor. And so I'm going to start at a current value, and I'm going to exponentially go down to 0. And again, we have this 5 tau here. So when we disconnect our inductor, again, it does store energy in terms of the magnetic field. When we no longer have a voltage being applied into source or current source, whatever it happens to be, we are then going to use that stored energy to go through and create a current that follows this graph here. We will see these equations here in a little bit, but something is a little interesting with inductors and how they go through and interact with the different shapes that you can have for your source. So before we look at that, any questions so far about the current in an inductor? So we're going to consider a square wave. So I understand this is technically a little bit closer to AC, but it does start getting us into this idea for how our inductor is going to behave. So here we have our source. It's got a little square in it to indicate that it is a square wave. And if we go through and we look at the response for the inductor, it is going to tell us that the inductor opposes a change in current that is coming from Lenz's law. So it's trying to oppose that change in current. So if the, oops, it'd help if I didn't put blocks over stuff. But so here we have the value for the voltage from our source. So if it starts at 0, then bumps up to 1 or 2.5, stays there, and then drops down to 0. With the inductor, it's always going through, and any time that there is a change, it's opposing that change in what's happening. So if there's no voltage being applied, there's no current flowing through that inductor. As soon as this jumps to the 2.5 volts, this is pointing in the opposite direction. It is opposing that change. We're then going to have a part where it goes through and we've reached 5 tau for our particular situation. We then have our change and it goes through and it has this interaction again. So with the square wave, we are going to start, and when we get to the AC stuff, this is going to be where we go through and start seeing this relationship a little bit more. So this is what the graph would be typically represented as. If you want to go kind of see where this is derived from, I would recommend checking out example 1311, but we are not going to be doing square waves for this class. We're going to be keeping it with the sines and cosines, but it is just a nice way to see what is going on with the interaction between changing currents and our inductor stuff like that. So we'll do some more AC stuff here in a little bit. But let's go through and let's talk about our equations for the general RL circuit. So again, with the RL circuit here, our inductor and our resistor are in series with each other. And so we get these equations here. So let's talk about the general ones first. So don't look at those yet. So here we have our instantaneous voltage across our inductor, and then we have the instantaneous current for the inductor as well. With these two equations here, they look identical to those for the RC circuit if and only if we are using tau. So if, which we have here for both of the exponential terms, we do have the tau here represented. In the case of the RL circuit, which we are doing today, that tau value would be equal to L divided by R. So we need to make sure that if we have these starting equations, we understand what tau we should be using. One of them is RC, one of them is L divided by R. So if we go through and plug in our specifics, so here we're looking at the current inside of the inductor, depending on what we're doing with the source. So when we are increasing the current inside, right, so here we have the situation where our initial current is 0. So this is when we're putting our inductor, so we're closing that switch to the battery and current is first allowed to flow. So if that's the case, there is initially no current. Over time, we would build up to the fact that eventually we would have 1 minus e to, or right, this exponential term, which is roughly going to be 0, or should be 0. And we would get that final value. If we have charged our inductor and we're storing that energy in the magnetic field and we disconnect it, we get this bottom equation here. So again, you need to understand how to go through and use these two equations, the two general forms of the equation for our inductor. So we're going to do an example here. But before we do that, any questions so far? So we want to determine the time constant for this circuit. I understand this looks like the Wheatstone Bridge, however, and I would like to talk about why we're doing 29 here. This is very awkwardly one of the very common ways that you can go through and set up a Wheatstone Bridge. This is going to be one of the ways you can go through and kind of have those different sides interacting. Our end goal, right, we're doing the time constant, so that's going to be tau is equal to L divided by R, or in this case, it's going to be RT. So there's a couple different ways you can go through and do this. And this is one of the main ways that Thevenization of your circuit is useful when you have non-resistor components. So by using Thevenin's theorem, we are actually able to go through and solve this type of circuit here. So I want to talk about it more so than stress you out. That's right, we've been talking about the theorem seems silly, especially when you just have resistors. It is more useful when you get into RL, RC, or RLC circuits. We're going to talk about it for this one here. I am not expecting you to be able to do this for the exam. Just need to go through, talk about how Thevenin's theorem is utilized for non-resistor circuits. So what we want to go through and do is basically we want to go through and figure out a way to represent this particular circuit with our theorem. In going through and doing this process, that's going to allow us to solve for RT. Once we have RT, we can go through and we can plug that in here to get tau. So we need to Thevenize our circuit. So if we think back to what we were doing with Thevenin's theorem, right, let's go through and let's complete our circuit to make it a little bit easier. We did actually go through and do the Wheatstone Bridge previously. So that is, I think about what lecture we did that in. I think we did it for our lecture with Thevenin's stuff, whatever lecture that happened to be, but right, you can go through it. It is one of the main ways that people like to go through and utilize it. So what we need to do here is just going to be different because now we have an inductor in here. So does anybody remember what the goal of Thevenin's theorem was? We wanted to take our circuit and simplify it to what two components?
Single load resistor and voltage source.
Mm-hmm. Yeah, so it's going to be a single resistor, and then you had your, right, we typically drew it represented with the open, that's where the load would go, and then we had a source. It looks a little bit different when you go through and have that inductor, because if we think about what we learned before, right, we would take out our load resistor to go through and find all that fun stuff. Which one's the load resistor? None of them are technically the load resistor. All of them are important resistors for going through and utilizing. So basically everything we learned about how to Thévenize the circuit doesn't work the second we put a inductor in here. You would need to go through and learn all new rules, which we don't have time to cover in this class. So if you want to talk about it outside of class, I will be happy to do so. But because we're not going to do this, if you're okay with it, I'll just ask you guys to trust me. And we'll go through and see what the Thevenization of the circuit looks like. Sound okay? Okay. So if we Thevenize our circuit, we get to go through and have the awkward ability to do this twice. Because it turns out, if we go through and do it, we're gonna get R1 and R2 together, and we can do R3 and R4 together. And does it look like they're in parallel? Absolutely not, but when you do Thevenin's theorem for having an inductor in here, so let's call this R, let's see what the RTH1. This is going to be RTH2. Yeah, with having this inductor, we get to go do it twice, which means we have two sources that we would go through and utilize. So the one on the left here is going to be 7.5 volts. The one on the right, 10.1. RTH1 is going to be 1 over R1 plus 1 over R2 inverse. And RTH2 is going to be 1 over R3 plus 1 over R4 inverse. So you get to go through, right? You do Thevenin's theorem twice to go through and get your values. And then once you have them like this, the way that you would go through and treat it, even though that there's an inductor in here, is you'd say, well, if enough time has passed, this is a short. And if it's a short, what are these two resistors in? So to find RTH, I would take my my RT, not RTH. I take my Thevenin's resistance for basically the left side of the Wheatstone bridge plus the value on the right side. And again, you do not need to know how to do this for this class here. So, and we're going through, we are utilizing this. So this will go through and get us the values. At the end of the day, we need to convert this into ohms. So there's two different times we can do that. We can do it now when we're plugging in the values, or we can do it at the end once we have our results. Right, both methods work out the same way to go through and deal with it. So just because I don't want to have to write out times 10 to the negative or 10 to the 3 every time, we're just going to do it in ohms. And we'll switch it over to kilo ohms at the end, or out of kilo ohms into ohms at the end. We'll have 1 over, sorry, 1 over, how did I write this? Oh. 1 over 47, sorry, 4.7 plus 1 over 4.7 inverse plus 1 over 3.8 or 3.3 plus 1/6.8. Inverse, taking that and plugging it in, assuming I did this part correctly. I got 4.57 kiloohms. Or if I wanted to go through and plug it in, 4,570 ohms. Any questions so far on 29? So now that we have this, we are able to go through and find the time constant. Do I need to worry about any other conversions? So I do my 3.3 times 10 to the what henries? What is milli? I'll have my -3 divided by 4,570 ohms. Should get us, with rounding, 0.722 microseconds. You are always welcome to leave it in seconds. You do not have to put it in microseconds. So if you left it in seconds, you would have tau is equal to 7.22 times 10 to the -7 seconds. So both of these answers are valid. Why don't they put it into 722 nanoseconds? I don't know, but that would also be the same amount of time. So leave it in whatever you're comfortable leaving it in. I'm not expecting you to sevenize any circuits that have inductors inside of them. So don't worry about the RT part, but are there any questions about finding tau? So it's the same circuit. So we have already very conveniently figured out the tau value, where if we didn't round it, would be equal to 0.72182 microseconds. So how can I go through and find the inductor or the current in the inductor 0.1 microseconds after the switch closes? Which equation should I use?
So,
Why?
because
You're right.
If the
Why?
switch closes, then that current is going down, which means that inductor is gonna try to counteract it, so
Mhm.
it's going up.
Yeah, so because right with it open, we're assuming we are starting our inductor with no energy stored. So when I close that switch, we are technically starting here in the increasing part to go through and solve. We can also go through, and if we wanted to, technically start with here, where we would just say, hey, there's initially no current. It would then simplify down to this equation. So both of these are valid starting spots for going through and utilizing it. Based off of grading your guys' previous work, if you guys can skip a 0, you typically do so. So we'll start with our equation here. I is equal to IF, 1 minus E to the -t divided by tau. So we solved for tau in doing number 29. What is our t value? So what units should I keep my tau in? Like what units do we want to use, right? Because we can convert it all to seconds, we can do it all in microseconds, we can do it all in nanoseconds. As long as they have the same unit, doesn't matter. So we're just gonna ask ourselves, which one do we want to do?
microseconds.
Okay, we're just gonna keep it in microseconds. So technically, we should use those extra sig figs and going through and doing that. What's IF? I need that to find that instantaneous current value. So how would I solve for that?
You just take your source voltage and the total resistance, and figure out what the current is, it's coming from the battery.
So if we're looking for the final value, this is gonna be where our inductor acts like a short. So if this is a short, that's just the nice ideal wire here. We already technically found this RT value, so we would be able to use that directly. We'd have our 15 volts divided by, technically, we should probably use the ohm value here such that our answer pops out in amps. Or 4,570 ohms. So now that we have all of this here, are we good to go through and solve? Yeah, so right now it's a plug and chug for going through and doing it. So I just like to do it all at once because I just felt lazy when I was doing this. 7, 0 ohms. 1 minus e to the negative. What you'll see a lot, at least especially when I do it, is if I'm looking at my 2 times, they are both in microseconds. Those are going to cancel out anytime we have an exponential in our equations. Whatever's in that power needs to have no units associated with it. So often you'll just see the numbers in there and you will not see those units. We'll have 1 divided by 0.72182. Technically microseconds, but again, we don't really care about that. So if we go through and do this, I got that the instantaneous current at 1 microsecond was 4.264 times 10 to the negative 4 amps. So we can see that represented kind of in a couple of different ways. Sometimes, and this is very textbook dependent, because this is an instantaneous current. Again, we're using lowercase I for that. Sometimes you'll see after the value in parentheses, the T. So in this case, the 1 microsecond. Both are fine for this class. Just if you are taking more circuits later, be aware that some people will care how your value is represented. So 4.26 times 10 to the negative 4 amps. If we felt fancy, right, 0.426 milliamps or 426 microamps. All of these are the same. I have zero intention of making you use any specific units for this exam. So whichever one is fine here. Any questions about 30A? So for B, we're looking for what is the current after 5 tau has passed. Are we changing it? So for B here, with going through and looking at it, what do you think we need to be aware of for going through and looking at it? Are we opening the switch? Are we keeping it closed? What are we doing with the switch?
Keeping it closed.
We're gonna keep it close, right? 5 tau is passing. And so, right, we can go through and we can now find the values. So if we think about it, right, we're still keeping that switch closed. So we can technically use this equation here, where instead of just plugging in our tau value, we'll do 5 tau. We already solved for, actually, hold on. Yeah, well, okay, let's start, sorry. Right, we already solved for the, right, we already have our current value, it's 15 divided by this monstrosity, whatever it happens to be. We still have 1 minus e to the minus t divided by 5 tau now. With this being 5 tau, what should the exponential term in theory become, right? Because this is, we're considering this to be a long period of time. So in theory, what is this value? And what's 1 minus 0? And what is any number multiplied by 1? So without having to plug in anything else, right? When we get that 5 tau, the current should just be equal to the final. When we are increasing the current, so when we're closing that switch. If we had it connected to something else and then we opened it, then eventually when we're at 5 tau, we would say that the current would be equal to 0. So, right, we can plug this in, we can get our value, it'll pop out in amps. We are technically good to go for that. So, any questions about inductors in DC sources? So, talk about the phase relationship between current and voltage in an inductor. So this is our equation here. All right, so we're going to move into our AC sources. We have the induced voltage is equal to the inductance times the time derivative of our current. And we've seen a couple different ways with an AC source that we can represent our equation for our sine function. The main one that we are going to kind of see moving forward looked a little bit like this. So this was one of the last equations we saw for our currents. So here we have our instantaneous current, which is a function of time, is equal to the peak current times sine 2 pi frequency times time. So this is an equation for the current source itself. And if we go through and look at our graph over here, we are seeing the nice points. So we have when our sine curve is equal to 0, we're at pi over 2, pi, 3 pi over 4, no, 4 pi over 3 pi over 2. And then our 2 pi, right? All those points here are labeled. Those are labeled with their values, but in reality, with them, right, it's just talking about, man, how do we go from having a sine function and we take that time derivative? How do we know what function do we have? What is the time? So what is the derivative of sine. A positive or negative cosine. Yep, so you get to go through and do that. Technically, when going through and doing this, so let's say we took our time derivative. So if we have our di dt here, what should that be? We do this time derivative. Right, we do know it's going to be a cosine. But what happens, right? Technically, it's a chain rule. So what's in the cosine term after we take the derivative?
Gonna remain unchanged.
And what about the chaining part of the chain rule?
Are we assuming F and T are both variables?
F is the frequency of the source. That is a fixed value for the individual source.
So it would just be two pi F.
So we'd have I peak times two pi F. If we take the peak current, two pi, multiplied by the frequency, then we multiply it by the inductance value, because that is part of the equation there, that gets us a volt. So a lot of weird unit stuff happens in that, but if we're taking this derivative, multiply it by that inductance, just trust yourself that it pops out in volts. Or if you have, right, just if frequency is in hertz and inductance is in Henry, if you have mixed units, you would have to go through and think about what's going on. So with this, it does mean that we can have an equation for, sorry, that should be a peak. The peak voltage inside of our inductor should be the inductance times the peak current, 2 pi times that frequency. Or sorry, no inductance there. Sorry, I'm trying to remember what it is off the top of my head. No, yeah, the L should be there, yeah, oops. Yeah, we do have it in there, because then it's voltage is equal to the peak voltage times the cosine term. So be comfortable taking the derivative of sine and cosine, because we don't always have to have a sine function for our AC source. We could have a cosine function instead. So what is the derivative of a cosine?
Negative sign.
And then if we need to chain rule, it behaves the same way. So I guess before we get into that, any questions about the phase relationship so far between inductor voltage and inductor current? Can somebody remind me what reactance was for the parallel plate capacitor? Just conceptually, not the equation.
Like that's equivalence in ohms.
Because right with the reactance, it's kind of telling us how does, in the case of the parallel plate capacitor, how does the parallel plate capacitor interact with the fact that, right, we're constantly flipping the orientation of the charges on that capacitor. If we're going through and we're looking at our source here, right, it's constantly flipping directions, which means we are constantly technically going through and would need to be utilizing Lenz's law with our inductor. So it too has a reactance equation. So sorry, there's the phasors if we wanted to see what they are. For that, it is a negative 90 degrees because of the lead. Really did a great job animating slides today. But here we have the equation for our inductive reactance. So again, we're gonna be using the symbol X to represent reactance, subscript L to indicate the inductance. And it is 2 pi times the frequency of our source multiplied by the inductance value. And this is going to pop out in the SI units of ohms. And once we have our inductive reactance, we can go through and treat it like a resistor. So we go through and add all the values together. When they're in series, we inverse them and then, or inverse them, add them together, inverse it again when we have them in parallel. And we get another version of Ohm's law. Here we have the S. So again, that's going to be the source. So because it's AC, that can be peak to peak. It can be RMS with peak and average. So peak to peak and peak and RMS will be the most common ones that we see, divided by the total reactance of our inductor. So I promise with the reactance stuff, it is useful. And we will start seeing that a little bit on Thursday when we come back again to the RC circuit. And then all next week, we will just be dealing with reactances and how to go through and use them. So it is a lot more it's not super interesting for the types of circuits we're looking at this week, or today, I guess, and last week. But I do promise you, they are useful because it's a lot nicer to deal with everything in terms of ohms, rather than trying to go through and do everything in terms of Kirchhoff's loop law or Kirchhoff's voltage law. Because then we get to go through, do everything with voltages, with each one having its own unique equations with how it interacts with volts, versus this is just, hey, treat everything like a resistor. So start using reactant stuff Thursday, but before we do our example with reactants associated with inductors, are there any questions so far about inductors and AC sources? All right, so we are going to do 37 here. So there's a couple different ways we can go through and solve this one here. But before we do that, I want you to go through and look at the circuit and think about what's going on. What do we have in series? What do we have in parallel? How can we go through and start figuring out what is, or how can we go through and find that current for L2? Does anybody want more time just looking at the circuit in 37? All right, do we have anything in series, parallel? What do we have? What's in parallel? Okay, so if L2 and L3 are the same, or sorry, they're not the same, they're in parallel, what is the same for the two of them? Mhm. And in particular, that's the instantaneous voltage, but whatever symbol we want to use for that. Okay, what other pieces of information do we have for our circuit?
What's the current going into L3?
Okay, so we know I don't know why, if we only have inductors, we're calling it L3, but here we are. If we're going through and matching kind of how the current is described in the question itself, that's gonna be our 50 milliamps. What else do we have? Okay. That's gonna be 3 kilohertz. Anything else? What's that 10B? Mm-hmm. So for this here, we don't know if this is an RMS, an average, a peak, right? It's not explicitly stated. It just says it's 10 volts. So we are looking for the current through L2 at this exact instant in time. So with it, if this is a peak, that's a peak current. If it's an RMS, it's an RMS, right? They'll match whatever type it technically happens to be. We just don't know what it is. So with this question here, we kind of are at a little bit of a weird spot. Because there's no way for me to find the total inductance because I don't know L2, right? There's no numerical value given to us for L2, which means I can't just go through, figure out the total inductance and then go through and do it that way. So that method's not gonna work. So this, basically anytime we see that we have an AC source, we are gonna wanna go through and use the reactance. So for the reactance for an inductor, right, XL is equal to 2 pi FL. Why might it be useful for us to go through and look at the reactance to solve?
And you can use Ohm's law to find the voltage through that, which is gonna match L2.
So yeah, we can start going through, getting voltage values, and that's gonna help us find total current. So by going through and putting it in reactance, we can basically say, well, how would we have solved this if it was a resistor? So we do a little bit more legwork at the front to make everything look like a resistor, but then we can go back to all those things that we learned before with resistor values. So we can do this for 1, we'll have 2 pi. Let's talk about units here really quick. I have kilohertz and I have millihenry. So kilohertz is 10 to the what? Okay, and then milli is still 10 to the -3 from earlier. So 10 to the 3 times 10 to the -3 becomes what? Yeah, they'll cancel out. So in this particular case, we have an option of, do we want to go through and do, right, we can convert it, and we'll show it for L1, but we'll see for L3, if we don't convert it, mathematically, it'll still pop out in ohms. So we'll just see it represented both ways. 10 to the 3 hertz, 5 times 10 to the -3 Henry. So exponential rules, this will pop out as 94.248 ohms. Or we could have done 3 kilohertz times 3 millihenry. Knowing that they are both to the same power, we can go through and not convert it. 56.54 ohms. So we now have our two inductance values. We can go through and find the voltage across L3. So V3 would be equal to the current through 3 times X L3. Do I need to worry about units here? Yeah, so I've got, if I don't convert my milliamps, my answer is going to pop out in millivolts. And again, from grading some of your guys' stuff for the past like really 12 weeks of work, people tend to forget that. So it's best to go through and convert it. So we'll have our 50 times 10 to the negative 3 amps times our 56.549 ohms, which is going to go through and get us 2.8274 volts. This is the instantaneous voltage for both 2 and 3. Because we know that 2 is in series, or sorry, in parallel with 3, so they have the same voltage. Now what do we need to do?
Didn't you figure out the current going through L1 and then
How do I find the current going through L1?
I use the reactance and source voltage, 10 volts.
I can do it that way. Or if you don't like multiplication, what's another thing you can do?
Voltage source divided by itself.
You don't like multiplication / division, what do we need?
It's the fraction based off.
Yeah, so we could, so yes, we can utilize Ohm's law once again to go through and find that current. It's not gonna be 10 volts across L1. So what we technically should probably do first is utilizing Kirchhoff's loop law. Go through and find what is the actual voltage across L1. So let's Kirchhoff's loop law state again.
And your current equals 0.
That's the junction one. So what's the other one? As you go around a loop, what sums up to 0? So if we think about our loop, here we're gonna do it for 10 plus 10 minus L1, whatever that happens to be, minus L3, which we just solved for. So going through and rearranging this, we could have V1 is equal to Vs minus V2. Go through and get, or sorry, V3. And get that value. So we'll have 10 volts minus 2.8274 volts, or V1 is equal to 7.17-ish volts. I got very lazy working on this question, if we haven't noticed. So technically, yes, all my V's should be lowercase v's, but they look essentially the same, so we're here, it's fine. I'm tracking them with subscripts. I don't care if you use lowercase or uppercase v for instantaneous voltage, as long as you are consistent throughout the problem. So, because I preach consistency, I should probably do that a little bit. All right, so now that we have the voltage across V1, We do still have to deal with Ohm's law, but that is going to let us go through and find that current value. So before we do that, any questions up until this point? All right, so we are going to get the instantaneous current through one, going to be V1 over XL1, so our 7.17 volts. Technically with extra sig figs, but you know. Here we are, divided by the reactance of inductor one. And going through and doing this, if we plug it in as it is, our answer is going to pop out in amps. So before we talk about the answer, what do we maybe want to represent our current in terms of based on the original current or the original picture? Why? Yeah, so I need to do units consistent in some way, shape, or form. Either when I have my current pop out, right, it'll technically pop out in amps. If I do it that way, I'll then need to convert my 50 milliamps into amps. Or because this pops out as an ugly decimal, we can go through and just directly convert that into milliamps. That way, we can go through and just keep everything in milliamps moving forward. So if we do this, I got 76.1 milliamps with some unit stuff going on. Any questions up until this point? So what can we, so we now have 76.1 milliamps coming down here. So how can we find the current through L2?
Subtract 50 from 76.
So that's using, right, the junction law. So we got I2 is equal to 76.1 milliamps minus the 50 milliamps, or 21.6 milliamps. Any questions about 37? So again, anytime that we have an AC source, even if it's capacitors or with inductors, there's a really good chance you're calculating that inductance value. So go through, convert what you can into inductance. Then we can treat everything the same way we did with resistors. That's using current divider, voltage dividers, all that fun stuff, superposition, everything like that comes back when we go through and put it all into reactance. So that's all I have planned. So this is the end of the material for exam 3. For the lab tomorrow being Wednesday, it is just a review period. So if you have any questions, it is a great time to ask because Thursday will be new material that will be on the final.